Welcome to qnawire.
So we're told a CO molecule makes a transition from the J=1 state to the J=2 rotational state when it absorbs a proton of frequency F equals 2.3 times 10 to the 11 hertz. And we're asked to find the moment of inertia of this molecule from just this data alone. And then we have to compare that answer with that obtained in example 43.1 in the textbook. Well, we can approach this from the method of working out the energy of the photon, which will be the change in the two rotational energy levels between the J=1 and the J=2 state. So our change in energy, delta E, will equal, well, it'll be E subscript 2 minus E subscript 1, where 1 and 2 are obviously J values. Generally, the rotational energy of a diatomic molecule, E subscript J, will be equal to, we have the reduced Planck's constant h bar squared over 2 times the moment of inertia I, which is what we're going to be trying to solve for. And that will be multiplied by the angular momentum constant number J, multiplied by J plus 1. And as you can see, these values will be quantized solely dependent on this angular momentum quantum number J. So we can work out the value of delta E by subbing in E2 and E1. But we can also work it out using the fact that this will be the energy of the photon released between the transitions of this energy level, which in turn will be equal to h, our Planck's constant, multiplied by our frequency f, which we are given. And therefore, we can relate this hf with this expression for ej and then rearrange for I. So on the left-hand side, we're going to write hf is equal to, and now we want to write down delta E, which will be this EJ equation, just with both 2 and 1 substituted in for J, subtracted from each other. So that will be, well, h bar squared over 2I, multiplied by, well, starting with J=2, we have 2 times 2 plus 1, so that's 6. And that will be minus h bar squared over 2I, multiplied by, well, J=1, so that will be 1 times by 2, so that's 2. We can collect this constant value on the outside, and then that will just leave us with 6 minus 2, which gives us 4. So that will be equal to h bar squared over 2I times by 4. And of course, we can then cancel all of this down, just giving us 2h bar squared over I. So now we can rearrange for I, so therefore I will be equal to, well, moving the I up to the left-hand side and bringing the hf to the right-hand side, we have I equals 2h bar squared over hf. So let's plug in some numbers to that. We have, well, 2 times by the reduced Planck's constant squared, which is 1.055, times 10 to the minus 34 joule seconds. Of course, that will be squared. That's all over our regular Planck's constant, which is 6.63 times 10 to the 34 joule seconds, times by the frequency of the photon, which we are given as 2.30 times 10 to the minus 11 hertz, giving us an answer of 1.46 times 10 to the minus 46, and then our units for moment of inertia will be kilograms meter squared. So this answer here is pretty much identical to the answer that was given in example 43.1, but that example had a different transition between different J numbers. So what this tells us is that the moment of inertia is constant roughly between different values of J. And the reason is because, as we know that the moment of inertia is described, if we're referring to a point mass, we have our mass times by the square of the radius. So because we know that the mass is going to always be constant because we're using the same molecule each time, or the same atom each time rather, it must mean that this bond length is going to be pretty much constant too. So that's the significance of this result compared to the one that's used in the example.